It's essential to fine dining. Crystal on the dinner table. No, not that crystal, and not the glass shaker, but the white grains inside. Salt, one of the most common crystals. A mineral found in deposits underground, salt is the only rock humans eat, and found in ocean water. Salt makes up just under 3% of seawater by weight. In fact, the oceans were, for centuries, the main source of salt, used to flavor food and, before refrigeration, to preserve it. Then, and still today, seawater was collected in shallow pools, where sunlight evaporated the water, leaving dried salt, which was then raked up, cleaned, and sifted. A process so lengthy and difficult that salt was as valuable as gold. In fact, soldiers in ancient Rome were paid with salt, or sal, which is where we get the word salary. Any chemistry student worth his or her salt, a phrase with the same origin, learns the basic chemistry of salt, or more precisely, sodium chloride, a compound of the elements sodium, abbreviated Na, and chlorine, Cl. Actually, ions of sodium with a positive electric charge, which makes them technically cations, and ions of chloride with a negative electric charge, technically anions. Opposites attract, so these positive and negative ions are strongly attracted to each other and bond. Logically enough, it's an ionic bond to become sodium chloride crystals. What exactly is a crystal? A crystal is a structure of atoms in a regular repeating arrangement in geometric shapes. Okay, that's a little hard to envision. Think of chicken wire repeating hexagons, or a lattice fence repeating squares. The way molecules are arranged in crystals is actually called a crystal lattice. Now envision those shapes in 3D, not a square, say, but a cube. Sodium chloride crystals are cubes with 6 equal sides, which is another characteristic of crystals. They have symmetry. Their sides are equal, or mirror image. Several other commonly known crystals are also cubic, including diamonds. And if you can't afford diamonds, cubic zirconia. But crystals of zircon, the mineral zirconia comes from, basically tetragons, 4 rectangles and 2 squares. Sugar crystals, they're oblong and slanted at the ends. What about quartz and a great deal of sand, which is quartz and other minerals pulverized? Hexagons, 6-sided prisms with a pyramid shape at the end. The most common crystal most of us see every day, even if we see it in cube form, is on the molecular level also 6-sided or hexagonal, ice. In fact, the word crystal itself comes from a Greek word meaning icy cold. These different crystalline solids don't just have different geometric patterns, they have different strengths, different melting points, which explains this: why one crystal, ice, can be melted by another crystal, salt, sprinkled on an icy sidewalk, spread on an icy road. As with everything in chemistry, it's not just how many atoms of which element are bonded together into what arrangement, but how they are bonded. We already know that in salt, the force holding the sodium and chloride ions together is an ionic bond. So sodium chloride is an ionic solid. Ionic solids are hard and brittle with high melting points. That's the temperature at which a solid melts into a liquid. Ice is different. Ice is the solid form of water, H2O. Now, 2 kinds of bonds are at work in water. The 2 hydrogen atoms and 1 oxygen atom in each H2O molecule are bonded with covalent bonds. In water, H2O molecules bond to each other with hydrogen bonds. This makes ice a molecular solid, fairly soft with low to moderate melting points. It doesn't take long for ice cubes to melt, even in cool room temperatures. H2O's freezing point, the temperature at which it turns into solid ice again, is 32 degrees Fahrenheit, or 0 degrees Celsius. Adding salt to ice changes that. Salt dissolves into the ice the same way salt dissolves in liquid H2O, or water. Remember, sodium chloride is made up of positive Na+ and negative Cl- ions? Well, H2O is a polar molecule with one slightly positive side and one slightly negative side. Its opposites attract all over again. When salt crystals come in contact with H2O in the form of water or ice, the positive sodium ions are attracted to and surrounded by the negative sides of H2O molecules. The negative chloride ions are attracted to and mobbed by the positive sides of H2O molecules. Each salt crystal is broken into microscopic pieces, dissolved by and into the water. But the water isn't the same as before. The dissolved salt has lowered its freezing point from 32 degrees. The moisture on a salted sidewalk or road surface won't freeze back into ice unless temperatures are much colder, down to about 15 degrees Fahrenheit. There's much more to know about crystals: X-ray crystallography, light diffraction patterns, crystallographic defects. We hope this video has at least made the basics of salt and crystals clear.